All right. Thank you for coming. This was kind of a really serendipitous, scrounged together event. Part of the idea here is to get everyone working on computer stuff interested in biology stuff. So one of the just emerging themes of the next few decades is the increasing volume of experimental data generated from new techniques that are low-key breaking every constituent of the computer. And for people that are into that, part of the pitch today is like, hey, this is a greenfield space of really interesting problems across systems, especially these systems that are directly influenced by load of data, so databases, file systems, these things. A lot of the things you guys have studied and are good at can be repurposed for a class of very compelling problems that have impact on people. So we've just brought people from FutureHouse, the ARC, here at Latch, to talk about the detailed work they're doing, and don't really want to talk much more and kind of want to get in the meat of the stuff, but some brief housekeeping items. We're hiring people here at Latch, so if you guys like the kind of things that Aiden's going to be talking about, feel free to scan the QR code or find any of us up here. And then also, FutureHouse has open roles across all kinds of positions, I hear, so definitely check them out. I'll be putting these up at the end too, so don't worry too much about not catching them. And then based on the demand here, it's kind of overwhelming. We expected to have like 20 people here. It's like 150. There was 100 people on the wait list that we didn't let in. We'll probably do this again. There's a lot more material that we want to talk about. We built lots of other things, and then people at other companies have built lots of things. So we want to bring people again for more iterations. If you have a system you built or a project, scan this or talk to us, and then we can host you guys. Without further ado, here are the talks. Aiden's going to be presenting on a file system, Noam on a file format, James on some algorithmic stuff that I don't fully understand, so it should be cool. And then Abhi on scaling state, which is a really cool landmark paper in the past month or two. So let's pass it off to Aiden. Thanks everyone for coming.
Hello everyone, I'm Aiden, and I'm going to be presenting LData, which is a distributed file system built on Postgres and S3 that we built here at LatchBio. LatchBio is a company for storing, analyzing, and visualizing biological data. And unsurprisingly, the way of transferring that data, storing that data is files. Everything from genomics, protein, imaging, computational configurations, etc. They're all files, and every single part of our platform relies on files. So our workflow engine, files as input, output, intermediate results. Our interactive plotting notebooks, again, input, output, saving figures, making things for publications. These are all files. In developer environments, people just want access to all their files to run scripts over them, mess around with them, have that environment over all these primitives. And our sample registry, where we keep track of biological samples, which all usually eventually point to some tissue data or something like that. Again, a file. So we started building this product 4 years ago, and the core idea at the beginning was a browser UI for browsing biological data. So you could have this portal where biological data types were really the first class data type support in the system. So if you have a FASTQ file, you can preview it in this Finder-like UI, and you're going to see some useful information about the biological file type. If you have a protein file, you can open it and see the structure of that protein right there in the browser. So that was kind of the first feature that motivated us. The next one was people being able to bring their own storage and plug it into the system of viewing your data. So pull things from S3 buckets, which is primarily where people store data, and then every other bucket type. We also wanted an API just to interact with this data from different product areas, like the workflows product. And then a couple years down the line, we realized we wanted to create a file system that could just be mounted on a Linux machine, because in the developer environments, it's kind of a pain to copy in data, copy out data. You really just want your data there. So that was this distributed networked file system that we developed. So what is the design space of like distributed file systems? Really, there are two primary concerns. There's where does metadata go, the directory structure, the access restrictions on these files, and where does the data storage go? So where do you actually put the bytes that make up those files? So let's look at some examples. The NFS example is pretty cool because you just have this server that runs a file system, and then talks over the internet when you make calls on a remote machine to interact with that file system. So it's kind of the simplest way of setting this up. You just serve a file system over the internet that's running on one machine. This is nice because everything's in one system, but it's constrained by that one system. You have a single point of failure and you can't scale it super well. Another example is Lustre, which is kind of on the other side of this, where you have metadata servers and you have data servers, and each can scale basically arbitrarily. Like the really cool large-scale deployments of these have over 1 trillion files, 500 petabytes of data, 50,000 clients, all interacting with one file system, which is really cool, but it's also extremely complicated to deploy and maintain. Another example is S3FS, which is kind of a meme example, but it basically uses the key structure in the object storage to store the file metadata, and then it just stores data in S3 keys. Now, this is cool because it's infinite capacity, because it's, well, not infinite, but it's S3. But you have broken semantics because S3 doesn't support file system operations, and there's no coordination between clients. So it's a good thing if you just want to look at your S3 bucket on your local computer through the CLI. Then there's Objective-FS, which is a proprietary software, but we actually use it in a few places because it uses S3 to store both the metadata and the objects, but it uses a proprietary file format to structure this data so that operations are relatively fast. This is really cool because you just have S3 and client. There's no intermediate server. This also means that that server is coordinating all the file system operations, which means that it needs a lot of requirements for basically recompacting data in the object store. And if you have many clients, they actually all have to coordinate with each other to ensure consistency. So if you have 200 clients on a write-heavy path on a directory, LS can eventually take tens of seconds, which is unacceptable. So what are some of the decisions we made for LData? We decided to put our metadata in Postgres, and we decided to do data storage in S3. This was really built around user constraints. So our users want to bring their S3 or other object store data onto Latch. So how will we support that first class? We want to serve it over the web, via APIs, over Fuse, and we want to store lots of data. As I said before, mounting of customer data informed our S3 decision. And that's nice because data can actually stay in a customer cloud. We're working on a product now too where the data doesn't need to leave the customer cloud for processing. You have a seamless ingestion experience with S3 buckets being kind of the first class object, which is the object store. And cost is reasonable, right? There's intelligent storage tiering, and you get all this free durability from AWS SL service level objectives, which is really awesome because you don't need to build that stuff yourself. It does come with quite a few drawbacks. So these are mostly around the API. So atomic renames are missing, which means that if you move something in the bucket, it's really a copy then a delete. Objects are immutable. You can't write a range of bytes. You have to upload a whole object every time you want to make a small change to any key. And objects must be versioned because otherwise you kind of lose the ability to disentangle operations. Also, the default tools given by AWS are surprisingly slow compared to network and disk limits. S5CMD is a good example of implementing these operations kind of to the limit of the hardware and S3, but there are still some fundamental limitations where it can take seconds to head an object within a region. And on average, it's about 150 milliseconds, which is very surprising. So then we use Postgres as a metadata store. And we can talk about concurrency control here. How do we handle race condition sensitive or atomic code? We basically just do a transaction per piece of work. So all of our services store their state in the database. We can use this for locking in transactions. And we design each step to be atomic and retriable. One way that we build this is we use flags to mark intent versus doing a whole operation initially. Instead of recording a copy as a task, we make the metadata changes in Postgres, and we mark it as pending, and then we can show those changes to the user immediately and do whatever work we need to do after that downstream. This allows silly things like if you move a node, it allows you to rename it, allows you to change metadata on that node, even though there's an operation in process on that node. And it also keeps transactions short. Another nice thing about Postgres is that you have stored procedures. We can implement all our file system operations as stored procedures within our file system and kind of expose the standard API for interacting with it. You actually have access to diverse runtimes too. We kind of use the default in most cases, which is PL, PG, SQL, but they also have like PLv8, which is a JavaScript runtime, and we found that we've actually had to move some code into that because it's faster than doing CTEs or subqueries, which is very interesting. And yeah, as I said, we implement all our file system intent marking operations in this language. Another feature we use from Postgres is row-level security. So you can run code to authorize user actions on things like inserts, updates, deletes, anything that changes a table. This is very nice because you get this default secure option. And you can disable it for procedures that need to touch thousands of rows and can then handle their own auth. And then things like schema level constraints, like things you get through relational databases like foreign keys, and then things you get from Postgres like check conditions or consistency triggers. These are all very helpful if you run like a very schema-first company where everything's defined very clearly in the schema with lots of constraints, and you can go read that schema if you want to understand how a service should work. Another thing that we get from Postgres is we kind of get this free API layer. So we run PostGraphile, which is a GraphQL server, over it, and we can expose all those Postgres functions as an API for external clients and internal clients to use. We don't need a service to proxy things. We can just talk to everything through GraphQL. Another thing we get is PG Notify, which is built in PubSub, so we don't need to run another server for this. What we also get here is if you update something in the metadata tree, you can immediately push that to all the clients that are reading like that part of the tree. So every browser client gets real-time updates when you do a metadata operation, and they don't need to pull or do anything like that. But what are some of the drawbacks of Postgres as a metadata store? I think the biggest one that we've run into is lock management. So we want to run serializable transactions everywhere, so we can kind of assume that statements don't interleave. But this can take out a very prohibitive number of locks. And you need support on retrying, which can kick operations out that should be fast into these retry loops that take a very long time to resolve. So we found that we have to drop transaction isolation levels in many cases, which means suddenly we have to worry about interleaving operations and other things that other guarantees that you lose from dropping down from serializable. Another thing is resource sharing. So you can't control how any one user is interacting with your database from, like, let's say, a CPU perspective. It'd be really nice to say, hey, GraphQL user that is logged in with this account ID, they can't take down our database by running some really adversarial query. You can't just state that in Postgres, which means that you need to build those guarantees into the application layer. Another thing is scaling. So the scaling options are limited, and one thing to realize is kind of the way that people talk about horizontally scaling Postgres is by having more read replicas. But for complicated workloads, almost everything's on the write path. We use cache tables, and most of our file system operations actually need to make some metadata change. So we don't benefit from read replicas almost at all. However, the vertical scaling of Postgres is extremely strong, and it's kind of the officially supported Postgres thing. So we don't really anticipate having a problem there. We just anticipate vertically scaling forever and potentially moving something to the application layer if necessary. Sharding would be workable, but again, that would be annoying on the application layer. So kind of the original idea of using S3 was this foreign bucket mounting idea. So connect existing customers' KV stores. Customers expect basically a perfectly replicated S3 structure on Latch, and we have to maintain a one-on-one correspondence between these two things. What we do is every single account in Latch gets a metadata tree that we call our managed object store that stores objects in S3. But for this managed tree, we don't need to sync anything because it doesn't eventually have a view in S3. So we can do some optimizations. Like when you move something in that metadata tree, nothing needs to change on the back end. You don't need to actually move any data. For the mounted bucket, this is different though. And you do have to move data. But what we do is for every bucket out there on S3 or GCP, we have one metadata tree, and then accounts just symlink into it. So we only maintain one metadata tree per bucket on Latch globally. But let's talk about implementing this two-way sync for the mounted buckets. So we read S3 events through an SQS queue, and we read Latch events from a Postgres drop queue. And we basically have one command, which is called sync, which just looks at the state in each place and takes operations to reconcile them. So if an S3 object is removed, we set the corresponding LData node as removed. If an LData object is removed, we issue a delete command in the object store, and we wait for confirmation of that to finally delete the object. If an LData object is moved, it's trivial in the managed bucket case, as I said. That's just a metadata change and return. In the mounted bucket case, we have to coordinate a move with the object store to ensure good properties, like this is actually eventually atomic. So let's look at a move node. Let's say in the browser UI, the user drags and drops C onto B on the left. This calls a function called LData move, and the only thing this function does is mark intent of a future state. So what does that look like? We change the edge table so that C is a child of B instead of A. We create what we call a witness node at AC with remove true, and we set a copied from flag, or not a flag, a pointer, on ABC to that remove node C. This looks a little weird at first, but to understand why we do it is in S3, the data actually lives at the prefix A/C. And we eventually want to move that data from AC to ABC. That's kind of encoded in the copied from state. And then we eventually want to remove that source, which is why we set removed on that node. Okay, so we run this operation and we add ABC to the queue. What happens next? The queue has an item. A sync worker picks it up and schedules a copy job. This is just in a different service that monitors the copy. That's all that happens. Once ABC is created, we get a notification in the SQS queue. And we see, oh, ABC is created. That's awesome. And what we can do with that is we can unset the copied from flag, because we know that data is where it's supposed to be. So a sync worker picks it up, unsets the copied from flag, and then it says, oh, you were pointing to a node that might be dirty, so let's add you to the queue. Now the queue has an item, a sync worker picks it up and issues a delete command to S3. Once AC is removed, we get a notification. We confirm that node is not there in S3, and then we can just remove the node finally and confirm it. And so that's the last step in the operation. Now we have the properly moved node state eventually. So what are the takeaways from this? It was 5 state transitions to coordinate an atomic move. That is kind of a pain, right? It'd be very nice if S3 implemented that feature. And the latency on that, upwards of 500 milliseconds, but something cool is by breaking things up into these state transitions, as soon as the object copy is confirmed, all the further work is cleanup. The UI can actually show the final state already. Another thing to note here is that versioning allows us to make critical decisions. So when we do the metadata operation, we record the object version. And if the object version changes, we will change the action that we take. For example, if the object version is changed on a remove, you do not actually do that remove because that means somebody else uploaded to that key path. So that's why versioning is so critical. Otherwise, we would have all these race conditions where we could delete data that should not be deleted. And the system properties here are critical. Each of these syncs being idempotent means that we can just always trivially recover from errors by just rerunning everything in a tree. If the states are correct, it won't do anything. If they're bad, it'll move it into the correct state. And the whole idea of journaling here, which is not technically journaling, but we're just decoupling intent from action, where we log the intent in the metadata tree, and then we offload work eventually to these workers. And by writing down that intent as the only thing you need to do before you confirm with the user, you allow to show them some confirmation, and you allow that any action can happen asynchronously after that. Now I'll briefly talk about the Fuse interface that we made and challenges of implementing a POSIX compliant file system using an object store. The first thing is what even is a POSIX compatible distributed file system? Sure, there's a spec, but all these valid answers are it behaves like ext4, like the in Linux tree file system. Behaves like NFS, which doesn't even really behave like ext4 because it has relaxed requirements. It supports Linux syscalls. That's kind of the one we care about. So most Linux programs run perfectly fine over this and have reasonable performance characteristics. Closed to open consistency. How to use a file from multiple computers. Do you go for strike first eventual consistency? So are you okay, well, kind of expounding on that, are you okay with various views of file length by different clients? Are you okay doing things with in-flight writes potentially being there, or deleted files still held open? You have to think about all these questions and determine what's correct for your system. One thing that is immediately annoying is basically every single Linux program runs getAddr very many times, to the point that if you had to do a network request per getAddr call, programs would run prohibitively slow. So you have to cache all this locally. That immediately brings up cache and validation issues, which sucks because suddenly now you can get basically discordant state between clients. And what we choose to do is go with eventually consistent, so you can read stale data, but it'll perform reasonably, and eventually you will get that update that shows more recent modifications. Another thing is there's a lack of a rename syscall. So if you move a directory, what that does is it calls rename on every single object recursively in that tree. This is O of n metadata ops, but that's okay. We solve that by caching. But it's unbounded RPCs to actually move that data. Now, for the managed bucket case, that's okay. It's just like a small change in Postgres. If you have a mounted bucket, that's a pretty bad user experience because it goes through every file, tries to move it. Something has to happen remotely, which is an operation in S3, and then the next file happens. So that's kind of a bad UX, and there's not much we can do there. That's just kind of a limitation of this system and interfacing with like what the Linux syscalls look like. So some reflections. Using S3 for data storage, I think it get prohibitively expensive at some point. It's about $250K per year per petabyte. If you ran an object store like Backblaze, which is cheaper and still has all these features that we need, it'd come down significantly. But if you run your own hardware, you can buy a petabyte rack forever for $120K. So that's like a pretty big difference, given that you'd have that thing for over 10 years. Also on the performance side, it's high latency, all right bandwidth, but I think the biggest thing is like you can't change that. You just have to kind of deal with what you're given. And then the semantics are okay, but in many cases they fail. For example, small writes to large files. So if you had a block device that you could write to and write chunks and read chunks, you can make things much more efficient, but you would have to implement all these features that you get for free from S3 that really matter for us. Like load balancing, sharding data, replication, health monitoring. They're like, I don't know, 9 nines of durability, whatever it is. Then reflecting on Postgres as a metadata store, it's convenient and surprisingly practical, but it, I think, required more expertise than we expected to run this thing effectively with all the log management. After a couple months of that, I think we became pretty good at it, but it was surprising. The thing that I think we really got from using Postgres as a metadata store is that we avoided prematurely optimizing our system. We get all these guarantees by running this central transactional system that we can rely on for concurrency for all these file system operations where concurrent access is totally normal and needs to be coordinated somehow. We lose performance to systems that use a database with extremely low latency writes or something like that, but then you'd have to move a lot of safety into the app layer, which is a trade-off. So like, what would an alternative approach look like, right? You could run something like Cassandra, which is low latency, high throughput. It is truly distributed, so you can run nodes in many places. You'd use an object store for chunks, something like Dropbox Magic Pocket, what they use for their underlying like block device interface to store like all their data. And then you put these together in the application. So you'd build the file system operations around these primitives, locking, permissions, having an API, all of this. But then we kind of lose out on our core feature, which would be foreign bucket mounting, the thing that people really find us useful for. And we'd probably just hack that system anyways and then build this for more performant object storage. Maybe we will one day, but that's it.
So whoever has questions, pass the mic to them.
Can you say more about managed use cases versus mounted use cases? Like when would you use one or the other and what are the trade-offs?
Yeah, definitely. I mean, the obvious mounted use case is you're just pulling data from somewhere else. Maybe it's a bucket that's shared across your lab. Maybe it's a bucket you have read-only access to that stores like petabytes of sequencing data that you need to get access to, and then you want to use all that data within Latch. That's the mounted case. The managed case is everything else. If you see you open the UI and it's like this Finder interface, and by default it's all managed because we can manage that storage, which means we can do things way faster. And then if you mount a bucket, you kind of get this mount point that just points to the mounted bucket tree, and then you can go in there and access all this data. Yeah, so the default would be managed bucket, and then mounted.
It's like it already exists somewhere and then
Yeah, or if you want to generate data that then you use somewhere else, want to point that into another system where you want to have the key structure. Because sometimes you want it with us and you use it with other products, or you want that bucket to be introspectable by other people in your lab. Maybe that's important. Yeah.
Really cool work. I wonder
you.
if you can share if the competitors like 7 Bridges or DNNXs, how do they handle this situation, they also allow their customer to do like external S3 buckets, right?
Yeah, I can't say that much about our competitors, to be honest. I just don't know. I know they have some cool products. There's like they have like an EFS-like storage that they can use from like, I think Sakara has this for like their workflow system, where then you kind of share files among a Nextflow run. We have a different solution for that as well. I don't know how they deal with mounting data. I highly doubt that they allow all the file system operations on that mounted data. But if they do, then that's cool, and we should go look at that. Yeah.
All right. Wonderful talk. It's like a This was a 4+ year labor of love from Aiden and the team. So like a lot of blood, sweat, and tears, and just like customer exposure and things going down at midnight. Yeah. All right, next speaker. I think it's Noam.
Hey everybody, I'm Noam Teyssier. I'm a bioinformatics scientist at the Arc Institute. A lot of you here are not from biology at all, so I'm actually going to change my talk a little bit to talk a little bit about why this is important and why, like, the problem that I'm trying to solve. And it all kind of comes down to the fact that sequencing data is only going to get bigger. In 2000, when the first human genome was sequenced, it was insanely expensive, and now you can do it for $100. That used to be $1 million. So things are about to explode in file sizes, and we're about to have a huge amount of data coming through the pipeline just constantly. And this data is actually all stored in a file format that was invented around 2000. It's called FASTQ. It's the de facto standard for storing unaligned sequencing records these days. And this format is a plain text file with very little requirements. It has 4 lines sometimes, and it begins with this @ symbol. There's a plus sign in the middle, and lines 2 and 4 are the same length. The only requirements that require it to be FASTQ, which makes it a really flexible format with very little structural limitations, but it makes it really annoying to parse, and it makes it really annoying to actually scale. And the reason why is that record sizes are not fixed or deterministic throughout the file. So you have to parse records sequentially. There's no random access allowed. If you want to access like record 10,000, you have to parse all of the records all the way up to record 10,000. And for context, right now we're sequencing in the billions. And you need random access to actually scale things. It's also that made sense when it was originally designed, when we were looking at thousands of sequences, where it was plain text, just ASCII characters for nucleotides. This is really space inefficient, and it requires external compression for storage and decompression for access to the data. Compression is usually parallelized, decompression is not. Another kind of wrinkle is that sequencing technologies actually sequence 2 pairs of records at the same time. An R1 and an R2, where R1 is the first record in the pair and R2 is the second record in the pair. And the way that you keep them synchronized is literally just the position they show up in the file. So these paired files require synchronized processing across these record streams, which become a real pain once you start doing parallel processing. And for context, decompressing FASTQ can easily take 80% of the runtime in a lot of sequencing applications, which is ridiculous to me. The obvious thing that you would say is just like, well, let's just run it in parallel, right? The problem is that this is a single producer, multi-consumer model. Parsing is inherently single-threaded. Only the operations done on the sequences can be multi-threaded. So if your operation isn't significantly higher than the cost of reading and decompression, your consumer threads starve. And this is what happens a lot. You can have a bioinformatics tool, you say, I'll give it 32 threads, and you'll see it just saturates at like 8, 16, won't actually use the 32 threads. So even though your fancy 256 core CPU is there, you can't use it, you're stuck. So how to improve on FastQ. How can we scale this to something that can go from, that was built for thousands of records to now thinking about trillions of records? We need something that is easily parsable, easily parallelized, and natively compressed. And so this leads to the work on Binseq, which is addressing these fundamental limitations of FastQ. So Binseq is a family of binary file formats to encode sequencing data. There are currently two variants of the format. There's BQ and there's VBQ. And they use a property of nucleotides and the fact that there's only 4 letters in this alphabet to do a 2-bit packed encoding of nucleotides. So instead of recording every nucleotide as an ASCII or like 1 byte, you actually only need 2 bits and you can pack them into a byte. So you by just that, you get a quarter of the size. There's 2 versions of this. There's BQ, which is a little bit more limited and structured. It only allows for fixed length records. There's no quality scores, and there's sequence level random access. And then there's VBQ, which is a lot more flexible. It has variable length records for long read sequencing. It has optional quality scores and a block compression structure that I'll talk about in a second with Z standard and block level random access. So instead of individual records, you have access to blocks. So BQ itself is actually a very simple file format. It starts with a header that gives you the length of every sequence, and then you basically have all of the sequences. They're all just bit packed, and every sequence has a flag. So it's a kind of prefix to it that tells you, or you can encode some kind of information about it, like the group that it comes from, or maybe like the average quality score in it, just whatever information you want. And you can have 2 of the records side by side. So instead of keeping 2 files in sync, you can just have them in the single file and do operations that only operate on one mate or on both mates. Mate being the side of the pair. So because these files are actually deterministic, or the record size are deterministic, you can read the header and know exactly where every record is just by knowing the size of the file. So when you scale this, or you want to think about parallel processing, you can actually just memory map the entire file, and every thread can directly access a chunk of records and just read without any kind of contention. Each record has both R1 and R2, so you don't need to synchronize between the files, and every thread can just immediately operate on the records that it needs, which is nice. And then VBQ is a little bit more structured. Basically, it has a header, similar to the one before, and then it has a series of blocks. Every one of these blocks starts with a block header, which is not compressed, and it tells you the size of the block in its compressed form. And this is like a Z standard compression. Inside the block, you basically have a bunch of records. Each record says the length of the record and has some quality scores associated with it. And what you do then is you just compress the block. The block header tells you how long the block is, and you can easily build an index to go around it, just tell you where the starts and stops of every one of the blocks are. And then the block decompression can be done in thread. So you essentially get in-threaded, parallel decompression. So sequence access on a VBQ file looks like this. The number of blocks and the block positions in the file is determined from an associated index. Right now it's an external file that's just cheap to generate, but as an external file, something I'm working on is just putting it at the footer of the file. And then each thread can directly access the memory needs without contention via memory mapping. You memory map the entire file, you look for where the block starts and stops are, decompress, iterate over the records, and do something on each record. And that's what it looks like to use these. So let's see how Binseq compares to the de facto standard, which is FastQ. And the 2 biggest questions that most experimentalists and most people in bioinformatics think about are, how fast can I get my sequences? How soon can I act on them? And how big is the file itself? So these are the parsing and size benchmarks. I know that maybe it's not as easy for everybody to see, but basically this is the access time that it takes in seconds. We can see that the Binseq formats are at the top of this. Binseq and VBinseq, or BQ and BQ are all underneath even uncompressed FASTA and FastQ. And then if we look at the size of the files, they're actually significantly smaller than the uncompressed and are about, it depends on the file, but they can, in my experience, they end up being about half or a quarter the size of the compressed FastQ. And if you take the average score, which is essentially just a trade-off between both the runtime of access and the file size, we can see that they're all highest on this cost-benefit analysis. So they really hit that sweet spot of being really small and really easy to access the sequences without really trading off between the two. And if we look at the throughput comparison to FastQ using 16, I think this was 8 threads actually, we can show that BQ shows 40x to 10x throughput gains on parallel and sequential access, and then for VBQ we see 16 and 2x throughput gains for parallel and sequential access. Something that's important about this is that even though 40x and 16x are the throughputs that are shown here, this is measuring just the time it takes to actually access the sequence. For Binseq, you have to decode it from 2-bit back to ASCII. So for FastQ and for FASTA, you never have to do that step. So under load, you can actually see a much higher throughput gain because the unpacking time gets amortized into the cost of the operation you're working on. So let's see what this looks like on an IO-bound task. A really simple task is a sequence grep. You have, for every single one of your sequences, you want to just search for some subsequence that shows up within it. All you're doing is for every sequence, you just scan along that sequence until you find the subsequence that you're looking for. This is a really cheap operation and is kind of a classic IO-bound operation. And in this case, we can see that Binseq gets up to 80x and 50x throughput on this. In blue here, we see the FastQ on the x axis of this, we see the number of threads. This is just doubling from 1 to 128. And on the y-axis, we see the time in log 2. And we can see that both Binseq formats just continue to double in throughput, scaling almost doubling all the way to 128 threads for an incredibly cheap operation like this, while FastQ just absolutely levels out at 1. So this is a massive difference. On 8 billion records, which is kind of standard and like when you sequence with Illumina, doing an operation like this would take you 1.2 hours. And with this would take you about a minute. So that changes a lunch break into just like, I'm gonna go grab a coffee really quick. And now let's actually look at a CPU-bound task. This is a much harder problem. This is essentially something that doesn't starve the input threads. And the experiments that I ran here is I'm taking long-read DNA, long-read RNA, and short-read RNA, and I basically just wrote in Binseq to some existing aligners. One of them is Minimap2, and the other one is STAR, which is it's a short-read transcript aligner. And in this, we see the number of threads again on the x-axis, and the y-axis is the throughput in records per second. The solid lines here show you the FastQ throughput speed, and you can see that as you increase the number of threads, eventually you hit a saturation point. With Binseq, we just continue to scale. So all the way up to 128 threads, we continue to see a doubling effect. A lot of that is, we just continue to see a doubling effect. On the long-read whole genome sequencing, I would argue that this could probably even go to 256 threads, but I'm limited by our Slurm cluster. I'm not allowed to do it. So I would like to. So we could just continue to see this doubling, and if you are interested in using this tool, you can. It's called MMR. But a format by itself is not useful. What makes a format useful is actually building tools around it and building tooling and things like that for it. And what I've been working on is actually an ecosystem around Binseq to make it more useful. So there's BQ tools, which acts like SAM tools, and if people know that, if you've worked with it, it's basically a way to interact with these binary files. So it gives you interfaces to encode, decode them from different formats. You can count the number of records, concatenate them. You can grep for subsequence and just sample or subsample or upsample, things like that. Then there's a Rust library for actually reading, writing, and performing parallel processing. Yeah, this is like programmatic access, and I built this in parallel with a FastQ and FASTA parsing library. And in the trait system in Rust, you're actually, if you implement one of these, you actually get the other for free, which is very nice. So new tools that are building with the other library that I've built can get Binseq for free, and vice versa with Binseq and FASTA. And then underneath all of that is BitNuke, which is just a Rust library for 2-bit packing and unpacking with just like bit level operations like hamming distance and like is all SIMD accelerated. All of this stuff is free, open source, and looking for contributors. So looking forward, I'm adding more languages, hopefully. Right now there's Rust, C, and C++ bindings, but I'd love to get some Python and R bindings as well. I'd really like to reduce the amount of time spent in the packing and unpacking. It's really low right now anyways, but it's not yet at memory bandwidth saturation, so I think it could get even better. There's some really cool properties of Binseq because everything is memory mappable and you can actually pull ranges really easily, which makes it really nice for networks because you don't actually need to stream files directly. You can have different servers pull from different sections of the file and operate like that, which is, I think, a novel area in bioinformatics that hasn't really been explored too much. I'm also working on an optional 4-bit compression. So instead of 2-bit, you can get 4-bit if you want to encode more than just the 4-letter alphabet. And yeah, just a lot more tools just in general being built for it. So I'd like to thank ARC for letting me work on this, and thank you for the organizers for having me here, and yeah.
I think for those who have been working with FastQ, it's kind of incredible it took this long for someone to do this. This is a much needed problem and solution. Questions?
Hi, thank you for interesting work. So I guess like you touched on this a little bit in terms of, like the work that you currently have on developing, algorithms that work with this Binseq format. And I guess like related to that is like one important part of encouraging like the adoption of the format is how easy it would be to repurpose like the wealth of tools that we already have now working with FastQ to the new format. How easy do you think it is? Like how transferable would be like the context that we have in the traditional tools to transfer to Binseq? And also related to that, like have you done like benchmarking on prediction accuracy on, let's say, simple traditional tasks like variant calling from traditional formats like FastQ to Binseq, for example?
Yeah, that's a great question. So I'll start back on I'll kind of roll back. The last thing that you talked about was like traditional tools like on variant calling and things like that with Binseq. You were asking if like how it would compare against FastQ in that sense. I think something that's important is that a lot of the like things like variant calling are actually done on formats that actually come after unaligned sequences. So you do an alignment, you end up with like an aligned format like SAM or BAM, and then you do variant calling on pileups and things like that. So things that operate on sequences by themselves, they actually don't care what the sequences look like when they come in. A lot of them are built around streaming. So like things like every aligner is basically built around streaming, where you can essentially pass in just like from like a bash pipe, right? You can pass in your sequences and it can just operate on that. So you can do that with Binseq actually. You can just stream it and all of these tools can just immediately use it. But I think the real advantage comes from memory mapping and pulling sequences random access. And that requires a larger architectural change. And a lot of them don't, they weren't built for that in mind. Some of them were. So like Minimap, for example, is built around like an index, and then you query into that index with sequences. And then what they do is they stream, and then they query per stream, or per record in the stream. So it was actually really easy for me to wrap that around and make a Binseq wrapper because I have an index, I can query into it really simply. So I think that what I found is that tools that are built well are much easier to adopt this format. And then tools that are really, really built around the streaming format, I think will take a lot more work. That being said, a lot of the tooling right now exists in C++, and I think a lot of the maintainers of those tools are really frustrated with maintaining those tools, and there's been a big push towards Rust in the bioinformatics community. So I think that like there's actually been a lot of kind of rebuilding, like there's the rewrite it in Rust kind of meme, but like that's actually happening. And so people are actually using these libraries and thinking through these problems again. So I think it's actually a really nice time to kind of get this adopted into new tools.
Before you built the format, did you think about, instead of starting from scratch, maybe leveraging some table formats that have implemented, fast lanes or like other kinds of like compression standards for like bit packing and string compression, decompression, etc., and just putting your records in a table? How do you think about designing as a table?
Yeah, I can say that I didn't think too much about doing it in a table just directly. I think that I wanted a format that was easy to compose on the fly and I wanted a format that was really like simple to explain as well. There are a lot of advantages to having things in tables, but I think the streaming aspect of it the streaming write aspect of it, I think can sometimes be limiting. And when you're building these files, that's kind of a requirement for them because they come off of the sequencer, they get converted into this format, and you need something that can stream read, stream write, and then operate on these formats as well. That being said, I think Fastlanes is a really interesting project, and it's something that I'd be interested in maybe adapting or using and things like that as well.
I'm curious what applications in random reads in a batch of sequences.
Your question is random access?
When do you need to do if you have a billion sequences, when do you need to do very fast random access for maybe a dozen of them?
So the random access comes in when you want to parallelize an operation. So if you, for example, you have a billion records and you're applying a function per record, you don't, yeah.
But why won't you just in a block?
Right. So that comes back to the decompression of FastQ that's single-threaded. You essentially have to stream these records. You can move them into the block, but then you have to move that block into a thread. You have to deal with the memory movement, and you also have to wait for that whole block to come in, especially when you have synchronized records across two files.
Right. So if I have a billion sequences, why can't I just divide them into 10 blocks and compress it with FastQ gzip for 10 blocks and then parallelize my C++ tool on these 10 blocks?
You absolutely can, but then you have to deal with 10 different files and move them around and things, and you have to deal with 20 different files because there's an R1 and R2 for each one of them. And this is actually a strategy that's done by a lot of tools. A really popular tool is called Cell Ranger, which does single cell alignment. And the way that they parallelize their sequences is they basically just shard it. They just they take their big FastQ and they spread it across 128 different files and whatnot. The problem with that is then you end up writing that file, and on network file systems, it's ridiculously slow. And then you lose the compression ratio as well. So your file sizes actually increase, and then you double or maybe triple your file sizes required, as opposed to just having a file that you can random access into, just get parallelization for free.
Especially as people get nanopore sequencing online for methylation sequencing and for protein sequencing and stuff like that. Do you feel like this will scale well? Have you given any thought to that?
Yeah, I think 4-bit would scale really well for VBQ. I don't think it would scale for BQ. Right now I'm seeing that BQ is about half the size of compressed gzip, like FastQ gzip. If we do 4-bit compression, it would be about the same size. So we lose the data size there. But for VBQ, because we're compressing them in these blocks anyways, 4-bit doesn't really matter all that much. And then we get a lot more a lot more nucleotides that we can encode, and we can encode amino acids. We can encode DNA, and then invalid nucleotide like N as well. So I definitely think that there's a big use case there.
That was awesome, and as I said, much needed. Next, we're going to welcome James from FutureHouse, and while he's getting set up, actually the vast majority of our production workflows, especially the multi-day ones, spend a significant proportion in an IO bound state, partially because reading from these legacy file formats. To your earlier question, a lot of the time you don't really control what the biologist does. They're using these archaic FastQ and paired read conventions, and you don't really control how it's chunked up. So this lets you adapt or play well with the old guard as we phase in the new stuff. But this kind of work will speed stuff up a lot. All right, take it away.
All right. Hello, everybody. My name is James Braza. I work at a company called FutureHouse. We are a focused research organization based in San Francisco, philanthropically funded and trying to build an AI scientist. If you've been to FutureHouse before, raise your hand. I recognize some of you guys for sure. And if you work at FutureHouse, raise your hand. All right. The past year, I guess, we've been building several algorithms, and today I'm going to talk about them. These are algorithms that build on themselves in a concept from the AI ML community called recursive self-improvement. And I'm calling it the Edge of Tomorrow algorithm. If you've seen the movie Edge of Tomorrow, it's when Tom Cruise, who's playing this guy, William Cage, he gets trapped in a time loop. and he relives the same day over and over until he can save Earth from these aliens invading. There's a couple other movies where the same thing happens. Palm Springs, if anyone's seen it. Groundhog Day, this character Phil gets trapped by Punxsutawney Phil. And then Happy Death Day, which is when this woman Tree has to escape this masked killer. I'm a member of the SF Systems group, recently joined the SF Systems Club. I like systems thinking, and I think when you're doing your work in the MLAI community, a lot of it is systems thinking. And so the algorithms I'll talk about today are based in systems design thinking. The first class I would like to talk about is data flywheels. So data flywheels are algorithms where you start the day with better data every day. So the first one, simple one, is called expert iteration. Expert iteration, you start out with your initial policy. Your policy is your model. You can think of it as a llama 8B. The goal is we'll repeatedly supervise, fine-tune this model over and over on completions from the previous model, and those completions are getting better over time, and through more fine-tuning, your model gets better. So we'll enter a loop here with your initial policy. We start out with a batch of rollouts, which is basically prompting your model a batch B times, where each prompt is a different prompt, and you get a bunch of completions. Each completion has a reward assigned to it, and a higher reward is assumed better. So if you get a reward of 1, that's usually correct. 0 or -1 is incorrect. So one of the parts of expert iteration is you do this next step called rejection sampling. Rejection sampling is when you remove the wrong or incorrect or flawed outputs. And so here we can use reward. We'll just filter for not 0 and not negative rewards. Given that data set, we'll now supervise, fine-tune our model, and we get a new model, an updated policy. And we can use this updated policy to re-enter the loop and do another set of rollouts, and we'll repeat this loop n times. And at the end of it, we arrive at our final model. And this algorithm resembles the movie Edge of Tomorrow because Tom Cruise wakes up and he starts his day and he ends up getting killed by the aliens. He has better data and he restarts. And at FutureHouse, we used expert iteration last year in this aviary paper where we used it to fine-tune repeatedly Llama 3.18b. Iteration over iteration, here are the green lines here. Eventually it surpassed the frontier models of the day, GPT-4o, Claude 3.5 Sonnet. This is the general theme of recursive self-improvement, where you are piping outputs of the model back into itself. So the next one I would like to talk about is one from earlier this year. FutureHouse trained a chemistry reasoning model, and the algorithm here is called expert iteration reinforcement learning. And so it builds on previous techniques using reinforcement learning. We start out with our initial policy. In this case, it was an instruct model from Mistral 24B. You in your own data for the start of this one. We took our training data, prompted it to DeepSeek R1. DeepSeek R1 sucked at our task is novel chemistry tasks, and it got, I think, less than 10% accuracy, but that was all right. We just needed to start the loop. We'll use that, and we begin by supervised fine-tuning on, we supervise fine-tune our Mistral on that data, and we get a fine-tuned Mistral. From there, we'll enter reinforcement learning with verifiable rewards, RLVR. RLVR is a big buzzword, but basically the difference with supervised fine-tuning is it's one time offline, you blow through a data set. Here, every batch, our model is being improved in place for the next batch. And so we run a batch of B rollouts, and then there we run another batch of B rollouts, and each time the model is getting better, and we arrive at our updated policy. So this updated policy has gone through supervised fine-tuning and then reinforcement learning. So it's been updated twice. Now this is an expert iteration variant, so let's do our rejection sampling, filter out the incorrect. So in this case, we're using the RL portion to create this rejection sample data. Now we have maybe done many batches, so there's other things you can do. We filtered out times when the model used other languages. Sometimes it would speak other languages. We would go with the latest one, maybe hoping that's the smartest later on. and then you complete this in a loop. And we do this loop n times, and we arrive at, once again, our final policy. So in this loop, the difference with the previous one is it's even more like Edge of Tomorrow because we're starting with an initial policy every single time. And the previous expert iteration algorithm, we started fine-tuning the same model, but our starting point was more fine-tuned than the previous one. This one, it's actually the same starting point every time. The difference here is that our initial data is getting better. So this is actually pretty cool because that initial data is an external asset that you can then reuse, it becomes valuable, and you can apply it to any model. We use ERL in our Ether0 paper. Ether0 is our chemical reasoning model. And the reason we use DeepSeek R1 was to elicit reasoning in our non-reasoning starting model, the 24B instruct. So shown here, this first box, this is the fine-tuning, supervised fine-tuning. And then we did, we had all these chemistry tasks. We did 9 of them. You can see we start out low, get high, long story short. And then we did a second loop where all of the fine-tuning happens at everything all at once. And we were able to take 9 different tasks and basically through EIRL multitask train our chemistry reasoning model to be the best chemistry reasoning model in the world right now. And that may be controversial, but it's true. In my mind, it's true. So actually before I move on, I guess the general theme here we've talked about is improving our starting point, but in these Edge of Tomorrow algorithms, there's other ways. Because we're using systems thinking, we'll think of different ways. So perhaps instead of starting further ahead, what we'll do now is better pass our model data so that it can move much further in the same unit of time. We use this advantage-based curriculum learning technique. So curriculum learning is a big buzzword for trying to give your model easier problems to medium problems to hard problems. So as the model trains, the problems get harder. Here what we did is our chemistry problems were totally new problems. We had no general heuristic for defining their difficulty. So we let our model define the difficulty. And so what we would do is in our loops we've been talking about, in the previous loop, which you basically have for free because you already ran it, when we prompted the model, now we were doing GRPO. For those who, okay, GRPO is beyond the scope of this talk, but it stands for Group Relative Policy Optimization. What is a group? A group is basically concurrently prompting your model G times, where G is your group size. And the different items in the group, you can compare them and try to learn from the better performing members. Now, in machine learning, the term for better performing relative to others, and the relative is where group relative comes from, is called advantage. And so if no completion has an advantage above 0, if they're all 0, we can declare that it was too easy or it was too hard. Basically, the model didn't get any traction, we can't learn from it. But if that problem had a mixed advantage, meaning there was a problem that performed relatively better than the others, we can learn from it, and we declare it as non-trivial, it's medium difficulty. And so on this previous iteration, we built this buffer. So in this next iteration, we take our previous buffer and our training data, and we feed it some fraction of the time problems from your known learnable problems. So basically, what does this mean? This means in the previous iteration, we memorized what problems we could learn from, and then we just refed those problems in the next iteration, and it's totally for free. And it's actually really well. So this blue line here is without this technique. And we can see that about 30% of the time, it is, throughout the whole training, 30% of the time, it's only learning 30% of the problems. Those are the non-trivial ones with the mixed advantage. But when we use our technique, the curriculum learning, this advantage-based curriculum learning, we bump up to 50% throughout the whole training. So 20% of the time more, the whole training, literally for free. And how does it actually work in practice? This other plot is the evaluation rewards. We see the curriculum learning, pink line is above, but what it actually means in practice, let's look at the ending point. The final reward is 0.55. We attain that in half the time. So another advantage of this algorithm is it's just totally for free, and you get twice as good. So that's what I mean by these recursive self-improvement algorithms. They feed in, and then you can apply them for free. So if you're Tom Cruise and you want to beat the aliens, now you can run like twice as fast or something. I don't know what the analogy there is anyways. Overall, these are the 3 algorithms. Expert iteration, that was completed previously. In FutureHouse, we created the second 2, expert iteration reinforcement learning, and the advantage-based curriculum learning. Shout out to Sid, he's the first author on both of the papers referenced, and thank you for attending. Any questions?
Versus feeding it. I was curious why you did the rejection sample data technique to filter out wrong prompts versus feed that back in as like, hey, you got this wrong. So to not use that information that the model was getting something wrong and just totally filter it out and then just redo it.
Yeah, the question is like, there could have been learnable signal in the incorrect ones. Maybe you can like learn from the wrong ones.
Yeah.
Yeah, I think that's valid. I think that's totally valid.
Good. Cool. I was just wondering if there was like a reason that it was like polluting it or something, or if it's just maybe down the line you could try it, including that signal. Yeah.
I think in our use case, the wrong ones would be, so in the EI algorithm that I'm talking about, our task was an agentic task. It involved a lot of tool use. And so I think the model was just misusing tools. And if you only fine tune on correct tool use, it would help. But that's actually a great question, yeah.
Makes sense.
On your advantage-based curriculum learning model, are there specific tasks that it does better on than other tasks? Are you doing,
Yeah, the question is, the advantage-based curriculum learning, does it apply better to some tasks than other tasks? And the way it works is you start a problem, you find out if it was too hard or too easy, or if it was like medium difficulty. And in that sense, it can apply to maybe any problem. If the problems have all very similar difficulty, then maybe it is less useful, yeah. If the model is finding everything learnable or finding nothing learnable, then the advantage-based curriculum buffer, you need to get it hot, you need to get it warmed up, and if it's not hot and it's not able to get hot, then yeah, I think it wouldn't work as well. Yeah. Yeah.
I was curious. Super interesting. I was curious what kind of problems you ask it. Are they typically more like Olympiad problems? Are some of them open-ended? Are some of them even like problems to ask different kind of questions? Like maybe some context on that would be cool.
Say the last part again?
Like, would there be like any problems that like the right answer is almost asking the right question? Is there anything like that? I was just curious in the types of problems, yeah.
Yeah, so our tasks are, at FutureHouse, we have these scientific tasks. So it's, could be like, given half a molecule and that it needs to smell like flowers, provide the other half of the molecule. Or it's literature, question answer, sequence design. They're not incredibly open-ended. They're not like math. We actually have a team that makes these evals up. They are novel. They're made like within the last year or something by basically the evals team we have. But they're not like totally open-ended. Is your question, are they like super open-ended or?
Yeah, are they super open-ended? Are they super like closed, almost just mathematical? Like, are they somewhere in between? And maybe like, even how does chemistry as a subject like affect those kind of problems versus like physics versus math versus bio?
So this like reasoning model effort is interesting in the sense that you can, when you're training your model, you can choose to look at the reasoning or you can leave the reasoning totally unattended. And if you are actually putting the reasoning under the scope of your optimizer, the optimizer may affect the reasoning, but if you don't, the reasoning will be maybe more faithful, more natural. And The Ether 0 paper, the second algorithm, that EIRL, was a reasoning model. And I think that the problems we faced, which is reason a bunch about chemistry for free, it's your scratch pad, and then answer, that would apply to anything in the STEM domain. Now, in the paper, we did find that some tasks didn't get much advantage from reasoning, in which case those were just better suited to memorization. Sometimes it's nice to reason, sometimes you just spit out the answer. And I think that can apply maybe to different types of science problems, like maybe physics, you always want to reason, but elementary math, you need less steps. Yeah, maybe if you ask me that question again, I'd give you a different answer, but that's just my answer this time, yeah.
Can I go? Yeah. So I'm using a lot of this for a different problem. I'm using at Meta, a lot of the Ethero stuff. Have you guys experimented a lot with multi-turn RL? Because basically you can get like verification if something works or not, and then you reason it back, and like having that be something useful for it. I'm just curious because that's kind of the path I'm going down right now to solve our problems.
Yeah, that's where we're headed next to, for sure. That's definitely very interesting, where you do something, you get it wrong, you get signal, you keep going, basically, and you try again. Yeah. I think that's our next step. It's very interesting and promising. Yeah, that's science, I think. That is science. So it'll be good. Yeah.
Yeah, like what sort of practical tasks do you see this like over like basically working on immediately?
Yeah, the question is like, what sort of practical tasks do these methods apply to? I think recursive self-improvement is really cool. First of all, you have a model improving itself over time. And I think there's many opportunities for recursive self-improvement. As far as practical tasks, maybe if we look at like a software engineering application, if you can train your model to be a better software engineer, you can solve a new type of problem. And then you start again, and because you can do that new type of problem, now you can solve 2 more types of problems. So in general, it's about gaining traction and hill climbing. And anytime you want to hill climb, recursive self-improvement is pretty cool. And in general, I think like if you get the opportunity to think about how can I close the loop, that's just like really fun. Yeah.
Thank you. So that was awesome. Last but certainly not least, we have Abhi, and he's going to talk about systems problems scaling state.
Hey folks. My name is Abhi. I do ML research at the ARC Institute. It's a bio and ML research institute. Specifically, I work on building models, deep learning models of cellular state. Can you look at a cell and predict how it might react in certain situations, say under application of a drug or CRISPR gene knockouts, or different ways you can stimulate the cell? Today I'm going to share a little bit of work. Actually, mainly it's just issues I faced scaling state to massive data sets that are coming out today. I have some co-authors in the crowd, so I'll shout you guys out. I want to start by calling out AlphaFold, actually. AlphaFold was the first example of seeing a machine learning model that could reliably generalize outside of the training data to any capacity. And this came out in the first year of my PhD, so it was a pretty defining thing and inspired me to work on ML for bio. And what it shows is that you can map protein sequence to structure. This is an instance level problem, but it enables scientists to assess the effects of these mutations in protein sequence and then try to simulate what would the structure be as a result. Or in certain cases now with AlphaFold 3 and other frontier models, simulate biomolecular interactions. And so it enables the scientists to perform counterfactual predictions. That's really important for really iterating fast in science. And what about the equivalent in cell models? An in silico cell that could reliably predict how cell state would change as a result of a drug would accelerate therapeutics development. For example, you could take a cell set or a population of cells that's diseased and try and see if you can induce it to look more phenotypically young or healthy. Or you could take old cells and try to make them look young, right? And there's a lot of difficulties in doing this actually with the eukaryotic cell. And so you'll see a buzzword of virtual cell thrown around here and there. And this has been done before already using more dynamical systems approaches and modeling the physical different properties and processes that go on in the cell, specifically in prokaryotic cells and more simple cellular organisms. Doing this for human cells is obviously the holy grail, but it's difficult to scale these dynamical systems to the complexity of the eukaryotic cell. And so at ARC, we're looking at how can you use deep learning to try to simulate some of the effects of the eukaryotic cells. And there's companies today investing a lot of capital into this problem. So New Limit, for example, is trying to predict what genes can you upregulate or activate that can be expressed to then help reverse aging. Zyra Therapeutics is now launching its virtual cell initiative. And by the way, this is just these are random companies. It's but Zyra Therapeutics is trying to integrate virtual cell programs as well. They're trying to integrate them with their protein models actually, but they're building out kind of the single cell side of things. Tahoe Therapeutics is another recent startup that just raised their Series A, but they're focused on repurposing drugs on cancer biopsies and training virtual cell models there to see if you can predict the effects of drugs on at a sample-specific level. And you see this in AlphaFold in different protein models. You see a lot of different people converging to similar architectures, and there's a sort of commoditization of the machine learning there. Cellular perturbation models have not had that sort of foundation model moment yet. There's a lot of reasons as to why, and some of the main ones are there's lots of technical artifacts in the data. AlphaFold had the benefit of having painstakingly and expert curated protein structure data deposited into the PDB with really, really high quality control. Single cell data doesn't have as much quality control, and a lot of times metadata is inaccurate. There's what we call batch effects, where different reagents can be used for different experiments. You know, the way you measure the cell, honestly, the capture chemistry itself can change based off of what technology you use. These introduce different biases into the data that the machine learning practitioner receives. And these limit the ability to train a foundation model on all available single cell data and then use that for transfer learning in downstream applications. And so the analogy is similar to in NLP, when before people trained BERT on all of internet text, people typically did bespoke analyses with small models trained for their specific tasks. And so when trying to predict how a cell would change, we think of it as you can break it down into 3 different parts. The first is if I add a drug to a cell, there's going to be some true effect of that drug. Maybe it kills the cell, or maybe it restores some function of the cell. There's going to be some heterogeneity or variance based off of the cell state itself, right? Different cells can be in different parts of the cell cycle. A cell could be in mitosis versus, I don't know, some other part of the cell cycle. And then there's technical noise, different capture chemistries, different readouts. And so in our paper, we focus on what we think is a tractable task of maybe one step towards virtual cells, and that's focusing on gene expression. So when you measure out a cell at cell resolution, what you're actually looking at is sequencing that are then aligned to a genome. This is all upstream of what I do. Actually, Noam does a lot of this stuff at the ARC for us. But you align these to the reference genome, and you get these histogram featureizations of cells. This basically tells you what genes are more expressed versus what genes are less expressed. And so as you think about these cells, you can think about them as histograms, and the distributions of what genes are expressed are changing over time. So when you say you want to model a perturbation, what you actually are doing in our case is predicting how these gene expression distributions change for each cell. So a lot of the data that's been collected so far for this, I would say it's in the low data regime. You can look at this plot here that shows over years the mean, or maybe it's the median number of cells per publication. And this is increasing at an exponential rate. So Tahoe Therapeutics recently put out a data set that has 100 million perturbation data points. Just recently, Parse actually put out a 10 million single cell data set, and Zyra put out a 10 million single cell data set too, but if you talk to some of the PIs at ARC, they got into the field when measurements were of like 200 cells or like 500 cells, right? So you're seeing this exponential increase in the amount of data available. And this has led to inconvenient and unscalable tooling. There's been a great standardization in the single cell field, tools like ScanPy that really simplify analyses for someone like me coming into the field who doesn't know much single cell. But the fundamental issue is that when your data is so small, it lets you fall into bad practices because it's easy. And so in the case of single cell, a lot of the tooling behind it assumes you can load the entire data set into memory, for example, or you can subsample different parts of that data set really quickly because it's in memory, right? So these are what I would call unscalable, examples of unscalable tooling. The issue is that there's, I think James pointed out a sort of a data flywheel, but we're seeing this in our field as well here, where advances in AI, biology, and also capital investment are signaling what's going to be a really painful inflection point for practitioners in the field. So you have first biologists that are working on these breakthrough assay developments, right? Tahoe is able to do 100 million cells in a single experiment. That's kind of unheard of. And those training data are then used by people to train better machine learning models. It both enables the design of better models, and then also you're just putting more flops and data into the problem, right? So you get increased model capabilities. And once you have this better AI for biology or these increased model capabilities, that leads to more capital investment. A lot of that is due to hype, but also just like the capabilities of the models are improving. And this capital investment is, so here's some examples, right? Tahoe puts out the 100 million data set. That enables us to train models and see the first signs of what we think are interesting scaling laws in single cell. And then you see companies raising funds and or companies raising Series A and different VC companies raising funds to put back into the entire process. What that means is that, oh yeah, there's a lot of these companies now. And so what that means for the future, right? The previous generations of these data sets were thousands of cells to maybe hundreds of thousands of cells. And now the current generations of data sets are in the millions of cells to hundreds of millions of cells. And in our experience, we've seen this as kind of like a pre-BERT era to like a GPT-1-ish leap in capabilities. The next generation of data sets is going to be in the billions of cells and several billions of cells. To Noam's point, I think people are sequencing trillions of reads now. And to enable that GPT-1 to GPT-3 level leap, we need better tooling that can accommodate for these billions of cells. And so for the rest of the talk here, I'll talk about what was the pain points in going from these data sets that were meant, or these methods that were meant to handle hundreds of thousands of cells to going to hundreds of millions of cells. So state is the machine learning model that we worked on for predicting perturbations. It's trained on 3.6 million tokens, 3.6 trillion tokens, which equates to around 10 terabytes of tabular training data. For those in the single cell field, it's not all perturbation data. So a lot of this is learning the characteristics of single cell gene expression patterns in what we call like a pre-training phase. And then you train it on perturbational data after that. And the key innovation in the state paper was, can you group together similar cells? When I say similar, it means they're matched on some covariate or some metadata, and pass that into a big transformer model to then predict the treatment or perturbation effect. There's a couple reasons why we did it like this. We found that homogenizing what goes into the forward pass of the model over here helps the model learn conditional perturbation effects better. So if the model is always exposed to, say, heart tissue cells as the input, then it's able to learn perturbation effects better than if the input batch had heart cells and kidney cells and spleen cells. We find that really messes up the training dynamics and makes it more difficult for the model to learn. So already I've made some assumptions about what operations I'm able to do with my data here, right? The first issue is when you have 10 terabytes of tabular data, you can't load that all into memory, and you can't do these group by operations on specific metadata. So we switched from ANData to using H5Pi. This is basically just memory mapped data of the different gene expression histograms for these cells. Getting a little bit into the weeds of the model, but when you're working with single cell data, the measurement of the cell is actually destructive to the cell itself. So you're never measuring the same cell pre and post perturbation. So instead, the correct abstraction that we think to make is comparing distributions of cells. So you have a bunch of cells that we call control cells, and you measure their gene expression profiles. And then you have a separate set of cells that receive some drug treatment. And you then try to train a machine learning model that can translate one distribution to another distribution. This is why this idea of metadata matching becomes really interesting, because you want to learn a conditional transformation across these distributions. And so for each one of these forward passes and each get item call of the model, where you're picking a specific pair of cells to learn this effect on, you have to actually sample a metadata matched cell, like the same cell type or from the same donor, for example. So this turns out to be really slow. And you can hack away at it a little bit, which is what we did at the state paper, right? So given a heart cell, you can cache in your data set what are all the indices within this data set of all the other heart cells. And then you can randomly sample from one of the other heart cells. And it works when you're segmenting indices for very simple group by conditions, right? If you want to stratify by cell type, or if you want to stratify by donor. Where this issue starts to become a little bit more of a problem is in the future generation of models, where you want to stratify by more complicated conditions. So if you want to stratify by tissue and by donor, or by cell type and by donor, you're having to store a lot of things into cache and having to segment the indices a lot more. In our case, because in state we focused mainly on learning cell type specific effects, we only had to stratify the data by cell type. And we made a repository cell load that basically all it does is it takes AND data and converts all of the strings into integers, like unique integer representations. If you use H5Py, these are just the codes in H5AD files. And then caches the metadata. And we found that this led to a 10,000 times speed up in runtime on the naive approach translating from memory mapped AND data here. So it works in the case of the 100 million cells and actually reaches within 2x the runtime of just having the entire AND data in memory. So the overhead of moving to this approach is not that bad in favor of scaling to larger data sets, even when in-memory approaches are feasible. Evaluation is a completely separate issue from training, though. So training in deep learning, you can do things mostly at the batch level. So all you need to do is load in one batch from disk into memory, and then you do your model, you do your backprop, and you're good to go to the next batch. But evaluation in single cell is a whole other beast. So a lot of traditional single cell evaluation methods require loading the entire data set into memory. Sometimes this is really not needed because a lot of the metrics that are actually being computed actually just take population averages. And so you actually only really need the average sometimes. You don't need to load every single point in your tabular data. There were a couple tricks along these methods that we did. One big one was also differential expression analysis. So some of these statistical tests can be parallelized across multiple threads. And so we implemented some of these in our paper to scale evaluations to, I think, 20 million cells for the Tahoe data set. So cell eval is a package actually that Noam wrote, and it took our eval time from 72 hours down to just 30 minutes. And so some takeaways from this, whenever possible in your single cell workflows, use GPU acceleration. NVIDIA is investing a lot of money into this and a lot of engineering resources. So it was helpful for me to use this whenever sanity checking or doing such. Use half precision whenever possible for your evals. A lot of times you don't need full precision and it cuts your memory by a lot, especially as you work with evaluating on some of these data sets. But also be careful when casting to NumPy because half precision in NumPy is really jank and not as well fleshed out as in PyTorch. And then lastly, parallelize your operations whenever possible. It's really difficult to fit everything into memory, but if you can split your evaluations by cell type or split your evaluations by condition, then you can just parallelize that across a lot of workers. And a lot of times I find that single cell people are a little hesitant to do this, but in our case, taking some of these issues and dealing with them at the beginning of our workflows enabled us to move really fast in the development of state. So the Tahoe 100 million single cell data set was provided to several frontier research groups at the same time. And our approach to hacking on this data set was to spend a miserable 3 weeks on just setting up the tooling and how do you parallelize things as much as possible? How do you write scalable data loaders that are memory mapped? How do you do this metadata caching? But it really unlocked rapid progress. Anyone that's building deep learning systems knows that if your evals take 72 hours versus if they take 30 minutes, it's just a different league of how many ideas and model architectures you can hack around and try. And so if you're building these deep learning systems, build that stuff out first, and then optimize for your ability to feed data into the model. In our case, we found that following those two guiding principles of evaling fast and optimizing for data throughput in the model led to state-of-the-art performance across a couple of different metrics on different data sets. I don't want to go too much into the metrics here, but this one here is Pearson correlation. This is basically just what is the Pearson correlation of the gene expression you predict versus the observed data. You see some interesting scaling here as well. So on this right side here, we have the smallest data set, which is in the hundreds of thousands of cells range. And you see that state, which is this blue bar here, does similar to other methods, including other simple linear baseline methods. Once you move to the signaling parse PBMC data set, so this is signaling cytokines that are added to the cell, you see a larger improvement. So here the data set is 10 million cells, and you see a 47% improvement on this metric as compared to other baselines. And finally, on the Tahoe data set, you see, in this case, a 63% improvement as compared to other baselines here. So what's interesting is that building the tooling that enables these models, it's an interesting relationship between the two of them. First of all, you need more data to even differentiate what is a better machine learning algorithm. Like, we would not have known that state is a better algorithm on some metrics if we were just looking at the smaller data set. But in order to do that, in order to look and analyze at these larger data sets, you have to put in the investment into the painful data loaders and all the unglamorous start. And then this is just another metric here. This is a ranking of effect size of perturbations. This is basically if you apply a perturbation to a cell, how many genes are significantly up or down regulated in their expression. And this is like basically a ranking correlation statistic on that. And again, you see this sort of scaling as you increase the size of the data set. We see that state is better able to leverage the data. So looking forward, several different institutes have pledged to reach 1 billion cells. ARC has its own virtual cell atlas that it's growing right now, both in terms of in-house data and also an AI agent that we wrote that automatically curates data from publicly available repositories. Chan Zuckerberg has also launched its own 1 billion cell initiative. And then you have the private players, right? These guys are raising a lot of capital to do data generation as well. And so several billions of cells with perturbations are going to be available. And there's a lot of shortcomings in the methods that we wrote in developing state. And so one issue in, I think, some of these communities is there's no commoditization of this tooling. For example, when we were writing state, we wrote all of this stuff from scratch, but there have been similar efforts and other really good libraries for building some of these single cell data pipelines. So that's the first thing is there needs to be some commoditization and collective effort on building good tooling that everyone can use so people don't have to reinvent the wheel. In terms of cell load, there's a lot of room for improvement. So H5Py natively right now doesn't support concurrency. And this leads to a big issue when you're training on a lot of different files. You can look at this really horrific GPU utilization for state. You need something that allows concurrent access. And so this is something we're actually actively exploring at ARC now, is like, what is a system that enables better GPU throughput as you scale more data? And you also are going to need more complicated group by operations, right? A lot of what people are looking at now is like, how do you mix in natural language with some of these perturbation models? That sort of thing requires knowing the metadata about the cell, harmonizing the metadata about the cell. People are using AI agents to do some of this now, but the key takeaway is the systems itself, you can't cache every single possible group by. So you have to actually build better systems to load data on the fly. And lastly, I put a lot of blame on the tooling and the data, but there's this quote I really like. So AlphaFold was trained on largely the same data as AlphaFold 2. And Nobel laureate John Jumper says that AlphaFold 2 was mainly just better machine learning. And that led to winning the CAST competition and significant improvement over AlphaFold 1. So while there is a need for better tooling and better data, there's also a dire need in single cell for better machine learning methods as well to really make use of this next generation data. And then I just want to thank my collaborators. So this was a huge effort. Yusuf, our group lead, who's not here, but Dhruv, who's here, Noam, I think I saw Lishpa earlier as well. So thanks to all my co-authors, and thanks for having me, Shreya and Kenny.
Probably 2 questions because it's getting late. Everyone wants to eat pizza and stuff.
Hi. How do you see these models being used? Is it just a massive search that then tells you where to look, or do you see these models actually providing mechanisms and pathways?
I'm sorry, I can't hear.
Hello? Hi. Yeah, so I just wanted to ask, how do you see these models being used? Is it just a massive search that then tells you, where to look specifically? Or do you see these models actually providing you mechanisms and pathways of what kind of effects these perturbations are having?
Yeah. Yeah, so the question was, how are these models actually going to be used? And is it to search across maybe the space of perturbations, or is it to uncover underlying mechanisms of biology? I think the first application is more so search. I see a more direct path to search than understanding underlying biological mechanisms. Maybe the next generation of data will unlock some of those capabilities, but search is a problem I think is more tractable now. So like, what is the perturbation required to induce a specific phenotype? This is what companies are doing right now, right? So I think that's the primary use case I see.
Hi, Abhi. Thanks for the talk. I was actually interested in your thoughts on some of the benchmarking results that you showed and also what was showed in the paper. So obviously, state was outperforming the other baselines in most of the cases. But I was interested in the signals that you got for the benchmarking that's based on the differentially expressed genes, which are more often the things that we are actually interested about, because they are the genes that respond the most strongly to the perturbation, as compared to the transcriptome-wide ranking of the signals. And I think, if I remember correctly from the paper, the absolute value of the benchmarking results was better for the transcriptome-wide ranking as opposed to the DEGs themselves. So do you think that the strategy of training on cell sets might actually kind of reduce the the ability to actually predict things that we care about? You get better predictions at a genome-wide level at the expense of the extreme levels that we actually care about, and also what's the implication of how we think about how we should work with data quality and things like that in that sense, and machine learning model design?
That's a good question. I don't think you would want to sacrifice on genome-wide resolution. I think the goal is to build a model that is capable of doing that. I think what you get from the cell sets is a denoising, essentially. By being able to look at more cells at once before you make a prediction, the model can probably drop out bad cells or something similar to that. And I think that the reason that the ranking might be down is maybe actually not so much due to the cell sets, because we saw that that metric was not as variant when we varied cell set. I think that might actually be a separate issue from the distributional training on cell sets. I think the Spearman ranking is something we want to look into more, though. I agree it's probably the metric that a biologist would look at the most, right? Spearman, you're talking about the log fold change Spearman rank?
Yeah.
Yeah. So, yeah, it's a good question.
Thank you.
Yeah.
Yeah, I was curious about the wall clock time for your training run, and also, how many nodes, how many GPUs, that kind of stuff.
Oh yeah, sure. So for the smallest data sets, you can train a model to convergence in, oh wow, they're really partying. You can train a model to convergence on the genetic data sets in like, I want to say 3-4 hours. And that typically entails just on one H1. It's really low utilization actually because the model size itself is not very large. Most of the time comes from just, and on the signaling perturbation data set, that was in the next scale of maybe 10 million cells. That took around a day, usually. So not significantly longer. And Tahoe Tahoe was heavily I/O bottlenecked, so you'll see that in the GPU util, right? Even that model doesn't require so much VRAM, and we were usually able to train each Tahoe model in about 2 days. Yeah, and so that would be for, it's actually the model really struggles to overfit a lot of the time, which is good. I think there's a lot of inductive bias we're baking in that prevent that. On Tahoe, it was usually around 400,000 optimization steps. Yeah. So every single perturbation run here was single GPU. You only need one, and you can probably train it on like an L40. Definitely, yeah. Yeah. Okay, thanks.
I think it's really cool you got to come in and talk. Like, that paper took the whole field by storm, and it's really cool to see the internals of some of the tooling stuff that no one talks about. Waiting for Noam to rewrite H5 AD in the future, more performance. Just really quick, Shreya, come up and plug Greylock.
Yeah. So hi everyone, I'm Shreya. Really exciting to be co-hosting this with Kenny today. I'm a partner at Greylock focused on AI native applications and infrastructure, also former engineer. For those of you who don't have much background on Greylock, we're one of the oldest venture firms in the United States, turning 60 this year, have a long history of partnering with some of the best founders at the earliest stages, whether it's through like Facebook, Airbnb, and recently Figma, Palo Alto Networks, I can go on. And you might be wondering, like, Shreya, why are you co-hosting this event in like biotech and like bioinformatics, computational biology? I actually kind of have a background in like work in the space that I've done in like labs at Stanford and UCSF in the past. This is a really interesting area to me, and I've been also coincidentally running smaller systems reading groups at the Greylock office over the past couple months. Met Kenny at one of those, and he wanted to do a bio-focused one, and I was like, hell yes, this is such an exciting space right now, especially because of all of the recent advances in AI that have been like kind of going full force in this field. So this has been really exciting to co-host. And thanks everyone for coming.
Thanks, guys. We'll be here till whenever. I think we have alcohol even, so drink, eat pizza. Last plug is please sign up. We want to do this again. As you guys can see, this is such a sick space to do computing. It touches every field of computer science, and it's going to play a big part of all of our futures. So come join the community, as it were. And then I know at least are you guys hiring? Like for roles? Okay. So Arc Institute is also hiring. I apologize, I don't have. FutureHouse is open roles. Arc Institute's very well known. Just go to their website, talk to these guys. And then we're definitely hiring. So if come find me or Aiden or anyone if you liked what he talked about. But yeah, 3, 2, 1, break. Thank you, everyone.